Welcome to Course 2.2, Building Digital Models and the Applicability of Construction Products. In this course, you'll learn what building energy models are, how they are created, and how they help evaluate construction products. We'll look at the essentials of BEM, the differences between BIM and BEM, and how both systems work together to support design and performance analysis. You'll also get a clear overview of the main tools and workflows used in real projects. Let's begin. This is a fully online and self-paced course, designed so you can explore the content comfortably at your own rhythm. In this brief introduction, I will walk you through the purpose of the course, the main themes we will cover, and the overall structure of the modules. By the end of this short presentation, you will know exactly what to expect as you begin the course. The central purpose of this course is to give you a clear foundation in building energy modeling, and to show how digital models relate to the materials and construction products we use in real buildings. You will discover how material properties shape simulation results, and how these results support better design decisions, whether we are planning new buildings or improving existing ones. This introductory course also sets the stage for the more specialized topics that follow in the E4I training pathway. This course is suitable for a wide range of participants, including people who develop or test new materials, support digital modeling or digital twin initiatives, work in building innovation or sustainability programs, or are building research competencies for future projects. No previous background in BIM and BEM material modeling is required. You will be guided step by step. The course is divided into 7 concise modules. We begin with a short orientation, followed by an introduction to building energy modeling, its origins, its purpose, and its role within today's sustainability context. Then, we explore how BEM supports construction management, how BIM and BEM differ, and how they complement one another. You'll also be introduced to the main software tools used in energy modeling, and you'll learn how to interpret performance simulation results. Finally, we close with a module on BIM-BEM interoperability, focusing on what information can be exchanged between platforms, and what must be modeled differently. This course is closely aligned with the broader shift towards sustainability, energy efficiency, and data-driven decision-making in the construction sector. Building energy modeling plays a key role in meeting EU performance requirements and supports the evaluation and optimization of new construction products. By understanding how models behave and how material data shapes their outcomes, you will be equipped to contribute to evidence-based design, product innovation, and more efficient project workflows. Throughout the course, you will come across a selection of external links and reference materials that are meant to enrich your learning experience. Most of these resources are open access, and when a source requires paid access, it will be clearly indicated so you can decide whether you want to explore it. Since this is an introductory course, we will point you toward the key tools and software commonly used in this field. However, becoming proficient with these tools requires dedicated training, which goes beyond the scope of this program. Our goal is to give you the foundational knowledge and guidance you need to continue learning with confidence. Thank you for joining this introduction. You now have a clear overview of what the course covers and how the learning experience is organized. Let's begin with Module 2.2.1, which provides a clear introduction to building energy modeling, explaining what BEM is, how it works, and why it is essential for evaluating building performance and supporting sustainable design. I hope you enjoy the course. Welcome, and thank you for joining this course on building energy modeling. Throughout our sessions, we will introduce the fundamentals behind BEMs, explain why they are essential for evaluating building performance, and show how they support today's sustainability and decarbonization goals. Whether your background is in materials, construction technology, or performance testing, this course will help you understand how digital energy models complement physical measurements and real-world assessments. I'm glad to have you here, and I look forward to guiding you through this learning journey. In the following course, we will address the following objectives. 1. Understand the fundamentals of building energy models, BEM, their purpose and relevance in building sustainable design, indoor comfort, and energy performance assessment. 2. Briefly explain EU's broader sustainability goals, energy efficiency, decarbonization, NZEB or EPBD compliance, GHG reduction, and the importance of the application of BEMs to achieve them. 3. Identify and explain the key inputs that define a BEM and its differences between the Building Management System, BMS. Building energy modeling is the process of creating a mathematical and/or computational representation of the building systems. A model that is capable to simulate the behavior of the building's indoor conditions and its energy flows, such as heating, cooling, ventilation, lighting, equipment, and renewable systems, in a given time series resolution. Thus, generating a tool capable to evaluate the building's energy performance, support design decisions, ensure code compliance, and optimize systems operation. As such, in its Handbook Fundamentals, the American Society of Heating, Refrigerating and Air Conditioning Engineers, ASHRAE, Guideline 14, to 2002 classifies building energy models based on their modeling approach in three main categories. Black box models, or data-driven models, which are characterized by having an internal logic and interaction mechanism unknown to the user. In other words, in these models it is only possible to know the input data supplied into the simulation and the corresponding outputs or results. It is not possible for the user to know the way the model performs its internal calculations to reach its prediction. The main advantage of this kind of models is their computing speed and efficiency. However, to properly achieve their objective, they usually require to be trained in large amounts of data. Neural networks that use reinforced or deep learning techniques are characteristic examples of this type of model. In contrast, white box models, also known as physical models, are developed within carefully constructed simulation environments where the model's internal logic, programming, and calculations are transparent to the user. This means that the model's internal decisions are interpretable and understandable. Therefore, white box models are more suitable for applications that require transparency in predictions, or when the results must be compared with physical reality at multiple levels, describing in detail the different interactions between the simulation components. For this reason, their generation requires more detailed information about the building, i.e. its location, architecture, materials, components, and systems, and its border conditions, i.e. schedules, set points, etc. than black box models, making it necessary to introduce multiple parameters to define the whole building's behavior. Even if these models are more demanding in computational power, due to this physical and interpretable nature, they can be calibrated with less data. Clear examples of these models include linear regression, Bayesian networks, and physical equation models, among others. Finally, gray box models undertake a modeling approach that combines first principles physics with data-driven, or statistical methods. It sits between white box and black box models. In a general sense, these models are a simplified physics-based representation of a system whose parameters are estimated from real-world data, blending physical insight with empirical data to predict system behavior accurately with a mid to low computational effort. In a gray box approach, the model structure is usually based on simplified physical laws, but key parameters are identified or calibrated using measured data. Some examples of these models are RC networks, based on resistance-capacitance models, to represent heat transfer and thermal mass, state space formulations, or data-driven white box models whose parameter calibration is based on measured building data, temperature, power, etc. The International Performance Measurement and Verification Protocol, IPMVP, structures the procedure of performing energy measurements and building energy modeling in 4 different categories, or options, which are based on the scope of the model regarding its application and energy performance assessment. Option A and B, labeled as retrofit isolation, narrows down the measurement boundary to an individual system. This way, the modeling scope exclusively focuses on the evaluation of a particular element or component of the building system. For example, the study for a particular heating, ventilation, and air conditioning (VAC) equipment, where its components are evaluated separately from the building or under laboratory conditions. For the case of whole building energy performance evaluation, IPMVP suggests the use of either Option C, whole facility, which is based on the use of utility meters and/or other measurements obtained from the building, or Option D, calibrated simulation, which focuses on the development of computer building energy models that can predict the building's behavior and its system's energy performance. Under Option D, the BEM is required to emulate as faithfully as possible the real building conditions, that is, its thermal and energy behavior. Thus, the BEM should be calibrated to minimize the gap between simulated results and reality. Building energy modeling emerged during a moment of global change. In the 1970s, the energy crisis made it clear that buildings consumed far more energy than previously understood, and that this dependency carried both economic and environmental risks. At that time, there was no reliable way to estimate a building's energy performance before it was constructed. Decisions about insulation, windows, or mechanical systems were made with limited data, even though these choices could lock in energy use for decades. At the same time, construction materials and VAC systems were becoming more sophisticated. New insulation products, glazing technologies, and mechanical equipment required analytical methods capable of capturing their real behavior. Manual calculations were simply not enough. This created an urgent need for digital tools that could simulate how buildings respond to climate, materials, and operational strategies. These early models allowed designers, engineers, and researchers to compare alternatives, optimize material selection, and support performance-based decisions long before the building physically existed. The history of building energy modeling reflects a fundamental shift in how we design and evaluate buildings. At its core, BEM is a predictive tool. It estimates how a building will use energy under realistic conditions. Early tools were quite limited. They provided simple hourly estimates and only captured a small portion of the physical processes occurring in real buildings. But even so, they represented a new way of thinking, using data and algorithms to guide design decisions. As computing power increased, these tools evolved quickly. They began to incorporate the thermal properties of materials, internal heat from occupants or equipment, and the interactions between climate and building systems. Over time, models became more detailed and capable of analyzing complex building assemblies, much like how advanced laboratory methods allow us to study material performance in depth. Today's simulation engines integrate thousands of variables simultaneously and help us understand how combinations of materials, technologies, and control strategies influence efficiency and comfort. The first generation of digital tools, developed in the 1970s and early 1980s, marked a major step toward performance-based building design. One of the most influential was DOE-1, created by the U.S. Department of Energy. DOE-1 allowed engineers to calculate heating and cooling loads on an hourly basis, something that had been impossible with manual methods. At the same time, these early tools were constrained by the computing power of the era. Material models were simplified, and many real building behaviors, like thermal mass effects, dynamic ventilation, or complex control strategies, were either highly approximated or omitted entirely. Interfaces were technical and required specialized expertise to operate. Despite these limitations, these programs introduced a critical concept: evaluating building performance before construction. This idea laid the foundation for modern simulation tools and eventually became a standard practice across the industry. The next phase of development brought significant advancements in building simulation. During the 1980s and 1990s, DOE-2 became one of the most widely used simulation engines worldwide. It introduced more sophisticated algorithms to represent internal gains, lighting, occupancy, and mechanical systems, which was crucial as new building materials and technologies entered the market and required more accurate evaluation. This period also marked the beginning of integrating energy modeling into the design workflow. Although DOE-2 remained separate from architectural tools, it encouraged design teams to assess performance earlier, even during conceptual stages. For researchers working with materials, this meant that simulation could begin to complement laboratory testing, helping to predict how specific assemblies or combinations of materials would perform in the context of a full building. In 2001, the U.S. Department of Energy introduced Energy Plus, a new simulation engine built by combining the strengths of DOE-2 and BLAS. Energy Plus marked a major leap forward because it uses fully dynamic simulation. Rather than calculating heat transfer at fixed intervals, it continuously tracks how materials and building systems respond in real time. This approach significantly improves accuracy, especially for advanced assemblies or materials with time-dependent behavior. Energy Plus also introduced a modular HVAC framework that closely mirrors real-world mechanical systems. Designers and researchers can model individual components such as coils, pumps, fans, and controls, and evaluate how they interact. This detailed representation makes Energy Plus valuable not only for building designers, but also for experts investigating new materials, building envelopes, or system technologies. Over the years, Energy Plus has become the core engine behind many user-friendly simulation interfaces, supporting both industry practice and academic research. Its combination of accuracy, flexibility, and modularity has helped make performance-based design and material innovation a practical reality for modern buildings. Today, Energy Plus sits at the heart of a much larger ecosystem. Modern design software, commonly known as BIM tools, can now automatically generate building geometry and material data, passing it directly into energy models. This level of interoperability significantly reduces manual work and ensures consistency between a building's physical design and its analytical representation. At the same time, user-friendly interfaces like Design Builder and Open Studio have made energy simulation more accessible to non-experts. Design teams can now focus on performance outcomes rather than struggling with complex software workflows. Meanwhile, advances in automation and cloud computing allow thousands of simulations to run in parallel, exploring different material options, facade strategies, and mechanical system configurations in just minutes. Looking ahead, the field is moving toward data-driven design. Sensor networks, AI-enhanced calibration, and continuous feedback loops will make simulations more accurate and closely aligned with real-world building performance. This evolution supports the development of materials and technologies that respond effectively to global energy and carbon challenges, enabling designers to make informed, high-performance decisions from the earliest stages of a project. The European Commission proposed the revision of the Energy Performance of Buildings Directive, EPBD, on the 15th of December 2021 as part of the Fit for 55 packages. This proposal, COM, or 2021-802, established the framework for achieving a zero-emission building stock by 2050, introducing new definitions for zero-emission buildings, ZEBs, and refining existing definitions for nearly zero-energy buildings, NZEBs, and deep renovation. Building Energy Models, BEM. plays a central role in achieving these goals. Calibrated BEMs are capable of reducing what is known as the energy performance gap. In other words, they minimize the quantifiable difference between real measurements and simulated results, enabling informed decision-making across a wide spectrum of subjects related to the building's use and performance. Thus, these BEMs can become essential providers for the scientific, predictive, and quantitative foundation needed to minimize the risks in energy conservation measures design, policy regulation, building renovation, decarbonization of its systems, and optimization of energy-saving strategies. Supporting EU sustainability goals as key tools in the development of novel sustainable policies and solution assessment in both new and refurbishment projects. Two key examples where BEMs support these goals are: as a calibrated baseline model, which is an accurate or calibrated representation of the building in its current or as designed state prior to any retrofit. Developing such BEM enables the comparison of the energy performance of improvements after they had been deployed in the building. In other words, its purpose is to quantify savings or performance changes relative to the building's original or as designed conditions. And therefore, this model supports retrofit analysis, energy audits, calibration, and M&V measurement and verification protocols. On the other hand, a calibrated BEM could be used as a referential model, not to be mistaken for a reference model which represents a code-compliant, typical, or normative building used for benchmarking. Just as the baseline model, a referential BEM is an accurate or calibrated representation of the building in its current or as designed state. However, it allows the contrast or comparison of energy conservation measures and energy-saving strategies prior their deployment in the building. The calibrated BEM operates as a design tool used for assessing possible impacts of different solutions to be applied in the building and/or optimize them before they are deployed. The use of calibrated BEMs is not constrained to measurement and verification purposes only, nor to the design of energy-saving strategies. Additionally, when used in conjunction with the building's management system, BMS, a calibrated BEM can be applied as a fault diagnostic tool dedicated to analyze the performance of components from the HVAC system. In similar fashion, it can be used for model predictive control, MPC, using its calculated predictions as inputs for the building management system, which in turn allows for the application of demand response strategies or renewable energy penetration. Furthermore, this intimate relation between the BEM and the BMS system allows the study of non-intrusive, low-cost optimizations of the latter. A calibrated BEM can be used to generate operational schedules and establish optimal set points for the building's HVAC system. Finally, calibrated BEMs provide a sound foundation for the design and evaluation of building retrofits. Their application as baseline models can be used for quality control in construction and renovation. At this point, it is important to make a simple, but crucial, distinction between what a building energy model is and what comprises the building management system. As explained before, a BEM is a simulation tool that focuses on representing the reality of building physics. BEMs aim to emulate the behavior of the building's physics, including its indoor behavior and its energy demand. On the other hand, the building management system, BMS, is a centralized, computer-based system whose software can either be open source or proprietary. The BMS is dedicated to monitor, control, and on some occasions optimize a building's mechanical and electrical equipment in real time. In other words, it guides and operates different building systems such as HVAC, lighting, ventilation, security, and energy. Because BMS already have a complex network of sensors deployed in the building, this system could become an important data aggregator that operates in a two-way flow with the BEM. First, providing historical inputs to the BEM for training and evaluation purposes, and second, receiving and applying optimized solutions obtained from the BEM. However, many BMS systems have limited capabilities in this regard, i.e., do not have large data storage capacity, or limited communication protocols. As their primary focus is real-time operation of the building, thus, requiring some level of intervention to update their capabilities and work with BEMs. Building energy models are fundamentally rooted in building physics, which provides the scientific basis for how temperature and energy act within a building. When looking into the building's heat dynamics, indoor climate is closely associated with the building's demand response to various stress factors. These factors can be of external nature, like those generated by the weather, or internal, caused by occupancy, lighting, equipment, or other loads. The impact that these stresses cause on the building's heat dynamics is constrained by the building's envelope construction and mitigated by the internal comfort conditions established by either code regulations or the building's users. The result is the building's energy demand. In most cases, meeting this demand requires the installation of an energy support system known as the building's heating, ventilation, and air conditioning (VAC) system. The resulting energy balance is in fact a complex undetermined system subject to a great number of variables, some which are measurable and others inherently unknown. This challenge forces us to make educated assumptions when establishing the value of some BEM parameters to try to represent the building behavior. In a broad sense, the BEM uses these physical principles to simulate how a building responds to weather, indoor loads, and user constraints over time. To achieve this, we translate the building physics into mathematical models that can perform time series simulations. The key components of a building energy model are the essential inputs and structures that define inside the simulation environment how a building behaves thermally and how it uses energy. From a broad perspective, the key components that describe what the building is, how it is used, what systems it has, and how it interacts with its environment, can be categorized into three major groups known as the passive systems, which integrate the building's geometry and its envelope properties; its active systems, that contain the building's VAC systems and define its components; finally, its boundary conditions, which comprises of external and internal stresses, as well as operational constraints that define how the building is used. The building's passive systems, often referred to as the building envelope, form the first layer of interaction between the indoor climate and the external environment. The definition of the passive systems begins with the building's location and orientation, which determines the degree of exposure of each facade to solar radiation, wind, and outdoor temperature variation. Orientation influences solar gains, daylight availability, and the building's ability to shield itself from overheating or heat loss. The site location offers context, such as surrounding shading elements and local microclimate, which also plays a key role in the performance of passive systems. The building's geometry and thermal zoning further define how internal spaces respond to outdoor conditions. Geometry affects the surface area to volume ratio, influencing heat gains and losses through the envelope, while thermal zoning determines different usage patterns inside the building, and therefore influence air movement, heat storage, and comfort. A crucial part of passive systems lies in the correct introduction of materials, constructions, glazing, and fenestration systems within the model. Material properties such as thermal conductivity, heat capacity, and airtightness determine the envelope's ability to resist heat flow and store thermal energy. Construction details, including insulation placement and thermal breaks, affect the envelope's energy efficiency, its infiltration qualities, and condensation. Meanwhile, glazing and window systems control daylight, solar heat gains, and visual comfort. Their properties, such as U-value, solar heat gain coefficient, SHGC, visible transmittance, and shading, play a central role in modulating the thermal behavior of the building. The building's active systems encompass all mechanical and electrical equipment responsible for conditioning indoor environments and delivering the services required for occupation, comfort, and health. At the core of these systems is the VAC infrastructure, which manages heating, cooling, ventilation, and air distribution. These systems interact continuously with the building's passive envelope and, based on boundary conditions, respond to changes in weather, occupancy patterns, and internal loads. Defining the VAC system inside a BEM depends on the scope of model and its future application. In building energy modeling, ideal load systems are simplified VAC representations used to estimate the heating and cooling energy demand required to maintain comfort conditions without modeling detailed mechanical equipment. This approach is especially valuable during early design stages, sensitivity analyses, or research applications where the goal is to understand thermal performance, envelope behavior, or load profiles without the complexity of full VAC modeling. On the other hand, simulating real-world components like chillers, boilers, fans, or distribution systems requires the introduction of a hierarchy of different components that work together to meet the building's indoor requirements. Here, the introduction of VAC technical specifications and equipment performance curves plays a key role in defining the capacity and efficiency of each component, and therefore of the building's overall energy performance, shaping how quickly and effectively the system responds to thermal loads. Finally, in a building energy model, boundary conditions define the various external and internal factors that influence how the building behaves. Their introduction inside the simulation environment ensures that the simulation reflects realistic operating environments. Weather data, introduced as EPW files, provides the outdoor boundary conditions. It defines the external stress that the building must respond to. Outdoor temperature, humidity, solar radiation, wind speed, and sky conditions all influence heat transfer, ventilation needs, and the performance of both passive and active systems. Similarly, internal boundary conditions, such as thermal loads, are equally critical in the BEM, because they quantify the heat gains and losses that determine how much heating or cooling energy a building demand. These loads arise from multiple sources such as occupancy, lighting, equipment, and infiltration. Proper load modeling ensures that the building's VAC system is correctly sized, enabling informed decisions about design improvements, and providing a detailed understanding of how energy is used within the building. Equally important are the introduction of operational schedules and rule-based controls that govern how the active systems operate within the building energy model. Thermostat setpoints, flow actuators, and on and off controllers orchestrate the functioning of VAC components inside the simulation environment to emulate real-time conditions of the building. Together, these boundary conditions create the operational context of the model, ensuring that the BEM captures not just the building's physical characteristics, but also the real-world conditions under which it must perform. Before we conclude, I would like to acknowledge the organizations whose intellectual property supported the software and methods referenced in this course. We thank the U.S. Department of Energy for the development of Energy Plus, Lawrence Berkeley National Laboratory for the Therm Simulation Tool, Design Builder Software for the Design Builder Platform, and Affinovatic for the CE3X application. We also recognize ASHRAE for the regulations and theoretical guidance that informed many of the concepts presented. Thank you for participating, and I invite you to continue your learning in the next course. Welcome, and thank you for joining Module 2.2.2, Applying Building Energy Modeling to Construction Management. In this session, we will focus on the relationship between material data and the performance of a building energy model, and how simulation supports informed decision-making in construction and product evaluation. I'm glad to have you here, and I look forward to guiding you through this module. In the following training course, we will address the following objectives. 1. We will show the importance of detailing material properties inside a building energy model, and list the key properties required in the simulation environment for both opaque and glazing systems. 2. We will briefly explain the difference between steady state and dynamic material characterization, including their applications. 3. Finally, we will show how BEM supports product evaluation, improvement, and validation. Becoming a decision-making tool. This course examines how building energy modeling, BEM, leverage simulation data to support product evaluation, improvement, and validation, with a particular focus on material characterization. In building energy modeling, materials and constructions are related, but distinct concepts, each playing a different role in representing how the building envelope behaves thermally. The building's geometry and its internal volumes are enclosed by construction elements. These are composite assemblies created by stacking multiple materials in a specific order and thickness to represent real-world building elements. In that way, a construction might describe an exterior wall composed of 2 layers of brick with variable insulation layers, and air gap between them. The total performance, thermal resistance, thermal mass, and heat capacity of such construction element emerges from the combined properties of all its individual material layers. Each one of these material layers has its own thermal and physical properties, such as conductivity, density, specific heat, solar absorptance, and roughness, which determines how that particular material transfers and stores heat. In BEM, a material by itself does not form a building element. It is simply a definition of a single layer's characteristics. Since materials are the foundation blocks for construction elements, accurate material characterization is essential to correctly define the building's envelope, as well as for evaluating the performance of building products, comparing alternatives, validating assumptions, and sizing design. Inside Energy Plus simulation environment, materials can be classified according to their construction roles. For example, opaque layers, air gaps, glazing systems, infrared transparent components, no-mass elements, or phase change materials. Their definition within the simulation environment allows designers and manufacturers to understand how specific material choices influence the building's overall energy performance. Through rigorous simulation, especially by the use of a calibrated BEM, materials can be tested virtually under a variety of conditions, exploring different layer combinations, optimizing material thicknesses and position, and thus offering insights that guide product optimization and ensure that real-world performance aligns with expected outcomes. Defining a material requires detailed knowledge of their thermal properties. In the case of conventional materials, the 4 key characteristics needed are thickness, conductivity, density, and specific heat. When these are known, white box simulation environments, like Energy Plus, can properly account for thermal mass and evaluate transient heat conduction effects in opaque building elements. However, it is important to verify that the selected material properties align with the intended scope of the underlying heat transfer models of the simulation environment. Additional characteristics like roughness and thermal, solar and visible absorptance help to define the energy interactions of the material with its surrounding layers. This ensures proper modeling of surface temperatures, convective and radiant heat transfer, and defines the overall construction's thermal behavior. Therefore, the following properties must be properly established to define the thermal behavior of any material. Roughness specifies the relative ruggedness of a material layer. It is a key parameter on layers exposed to air as it affects the construction convection coefficients. In Energy Plus, it uses predefined keywords ranging from very rough to very smooth to allow the model to adjust how surface texture influences convection heat transfer. Thickness defines the material layer's depth in meters, measured perpendicular to the primary direction of heat flow. Conductivity describes how well a material conducts heat. It measures the rate at which heat energy flows through a material when there is a temperature difference, and its units are typically watts per meter Kelvin. A higher thermal conductivity means the material transfers heat quickly, for example, metals. While a lower conductivity means it resists heat flow and acts as an insulator. Density defines the mass of a material per unit volume, typically expressed in kilogram of m cubed. In building energy models, density directly influences a material's thermal mass, which is its ability to store and release heat over time. Specific heat is a material property that describes how much heat energy is required to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin, or Celsius. Its units are typically joules per kilogram Kelvin. Used alongside density and thickness, it helps to determine a material's thermal mass, that is, how much heat a material can absorb before its temperature changes, and how quickly it responds to temperature fluctuations. Thermal absorptance is the fraction of long-wavelength radiation, greater than 2.5 microns, that a material absorbs when radiation strikes its surface. This property influences the long-wave radiant exchange between surfaces, directly affecting both interior and exterior surface heat balances. Thermal absorptance values range from 0.0 to 1.0, with 1.0 representing a perfect, black body that absorbs all incident long-wave radiation. Solar absorptance represents the fraction of incident solar radiation that is absorbed by a material exposed to sunlight. Solar radiation wavelength ranged between 0.3 to 2.537 micrometer. It includes the visible spectrum, as well as infrared and ultraviolet wavelengths. This parameter is used when calculating the amount of incident solar radiation absorbed by exposed surfaces and affects both inside and outside surface heat balances. Solar absorptance ranges from 0.0 to 1.0 and is equal to 1. 0 minus the reflectance of the material, 4 opaque layers. Visible absorptance is the fraction of incident visible wavelength radiation that ranges from 0.37 to 0.78 micrometer, weighted by photopic response, that is absorbed by the material. Visible radiation has a narrower wavelength band than its solar counterpart, and is used when calculating the amount of incident visible radiation absorbed by various surfaces, affecting surface heat balance and daylighting calculations. Similar to solar absorptance, it ranges from 0.0 to 1.0, and it is equal to 1.0 minus visual reflectance of the material, 4 opaque layers. Having defined the key material properties, we can now address the subject of advanced or different material classifications listed in slide 4. Starting with a no-mass material. The introduction of this type of material in a simulation environment allows us to define a layer only by its known thermal resistance, R value. Thermal resistance is a measure of how well a material or building assembly resists heat flow. It indicates how difficult it is for heat to pass through a layer and is commonly expressed in square meters Kelvin per watt. The higher the thermal resistance, the better the material functions as an insulator. In building energy models, thermal resistance determines how much heat is lost or gained through envelope components such as walls, roofs, and floors. It is calculated based on a material's thickness and thermal conductivity. Thicker, low-conductivity materials have higher resistance. Accurate thermal resistance values allow BEM tools to model conductive heat transfer correctly, influencing heating and cooling loads, energy use, and occupant comfort. Air gaps in a construction are defined similarly to no-mass material. They describe the properties of an air gap in an opaque construction element by solely defining the thermal resistance of the air gap layer. On the other hand, an infrared transparent layer will only participate in the transfer of visible and solar radiation. It does this by doing a wavelength transformation and making all short wavelength radiation that is incident on the surface into long wavelength radiation, and having it participate in the radiation exchange. It is important to note that an infrared transparent layer is introduced as a single-layer construction surface and should not participate in a convective or conductive exchange between the zones it separates. In order to minimize this effect, its introduction in the BEM is accompanied by a series of convection coefficients applied on the surfaces referencing this construction. A phase change material, PCM, is a substance that can store and release large amounts of thermal energy by changing its physical state, typically from solid to liquid and back, at a specific temperature. During melting, the PCM absorbs heat without a significant rise in temperature, latent heat storage, and during solidification, it releases that stored heat back into the environment. In buildings, they can be integrated into walls, ceilings, floors, or encapsulated in products like prefabricated panels. PCMs help to improve overall building energy performance by enhancing thermal mass, stabilizing indoor temperatures, reducing peak loads, and improving energy efficiency by absorbing excess heat during warm periods and releasing it when temperatures drop. When dealing with advanced materials, like phase change, BEM calculation engines need to be properly set up. In the case of Energy Plus, temperature-dependent material properties require the use of the conduction finite difference solution algorithm. To define a PCM, first one must know the conventional material properties at 20 degrees Celsius. Additionally, the model must integrate the following advanced properties to describe a single process curve whereby a material moves from a crystallized to liquid state and back. Temperature coefficient for thermal conductivity, expressed in watts per meter Kelvin squared, which defines the change of the thermal conductivity per unit temperature excursion from the initial value at 20 C. The temperature enthalpy curve, whose function covers the entire temperature range that will be seen by the material. Lastly, the definition of the PCM hysteresis properties adds the hysteresis effect into the material, allowing the melting of freezing process to follow different curves, representing an effect that is commonly seen in actual building envelope phase change material applications. Unlike conventional materials, which deal with opaque elements, glazing materials refer to transparent components installed in openings and windows of a building. It includes not only the glass itself, but also the technologies and coatings applied to it, such as low emissivity, low-E coatings, gas gaps, and multiple panes, that together influence the thermal and optical characteristics of the window construction. Therefore, glazing plays a critical role in controlling solar heat gain, daylight admission, heat loss, and overall visual comfort in the building. Because windows are typically the weakest part of the envelope, thermally speaking, accurate glazing characterization in a BEM is essential for predicting realistic energy performance and identifying design strategies that balance transparency, comfort, and efficiency. The optical properties of a glass can be entered as spectral average set, where the values entered for solar and visual transmittance and reflectance are assumed to be averaged over the solar spectrum and weighted by the response of the human eye in the case of visual properties. However, it is preferred to introduce window properties in a more detailed fashion, using their detailed spectral data. In this regard, it is important to note that glazing layers may have different properties defined for their front and backside surfaces, where front side is defined as the surface closest to the exterior of the building for exterior windows. The key glazing properties that define the different layers of a window construction are: thickness defines the glass layer's surface-to-surface depth in meters. Solar transmittance, which is the fraction of incident solar radiation that passes directly through the glass into the interior. It is a key optical property of window systems and typically ranges between 0 and 1, where higher values indicate greater transmission of sunlight. Front and backside solar reflectance defines the fraction of solar radiation that is reflected from the surface of the glass layer. Visible transmittance, which is the fraction of incident visible wavelength radiation that passes directly through the glass into the interior. It is a key optical property in daylight calculations and typically ranges between 0 and 1, where higher values indicate greater transmission of visible light. Front and backside visible reflectance defines the fraction of visible radiation that is reflected from the surface of the glass layer. Infrared transmittance is a similar concept to solar and visible. It defines the fraction of incident long-wave radiation that passes directly through the glass into the interior. Front and backside infrared hemispherical emissivity describes how effectively the surface emits long-wave infrared radiation compared to an ideal black body at the same temperature. Its value ranges from 0 to 1, where 1 represents a perfect emitter, and 0 represents a surface that emits almost no infrared radiation. Unlike directional emissivity, hemispherical emissivity considers radiation emitted in all directions over a hemisphere. Conductivity, which describes how well the glazing material conducts heat. It measures the rate at which heat energy flows through a material when there is a temperature difference. Together these properties define solar heat gains, which affect cooling loads, thermal comfort, daylight availability, and visual comfort. There are other advanced properties for different glazing systems, like thermochromic glass. We would like you to refer to EnergyPlus Engineering Reference and Barclay's Window Technical Documentation for their introduction into BEM models. An accurate definition of BEM's constructions with reliable information on each of its material layers reduces unrealistic predictions of heating and cooling loads, misinformed system sizing, and flawed design conclusions. By ensuring that materials and constructions are defined with precision, BEM can provide a robust virtual testing ground where design alternatives can be assessed with confidence, especially after the model has been trained or calibrated. This accuracy supports evidence-based decision-making, helping designers select options that optimize energy performance, occupant comfort, and long-term sustainability. BEM are powerful decision-making and design tool that enables architects, engineers, and stakeholders to explore and compare design options long before physical construction begins. In both new builds and refurbishment scenarios, BEM helps evaluate the impact of envelope upgrades, FAC improvements, passive strategies, and operational changes in a non-intrusive way by predicting how each choice affects energy performance, comfort, and long-term operational costs. In retrofit scenarios, BEM is particularly valuable because it allows practitioners to test different renovation strategies, such as adding insulation, improving glazing, or modifying system controls, without the cost and disruption of trial-and-error interventions on the actual building. For instance, it allows the assessment of an optimal thickness of a layer, as well as its position inside the different layers in a construction. This can be performed by contrasting the simulated results between the model with the material changes against a reference standardized model. But it is also interesting performing this analysis under a defined set of known, or previously metered, boundary conditions using the BEM as a referential model. In this way one could evaluate the effects that the changes would have produced under pseudo-real conditions, offering new insights into the behavior of the material and its dynamic performance contrasted against known outdoor and indoor conditions. The definition of material properties allows a steady-state characterization of their properties. The steady-state analysis of a material or a given construction assumes that heat transfer conditions do not change over time. Instead of tracking how materials store and release heat, steady-state methods evaluate the instantaneous rate of heat flow through materials under fixed temperature differences, which are usually set based on standards and regulations. This first step in analyzing the material is commonly used in early design stages, code compliance checks, or quick assessments where detailed thermal mass effects are not required. Steady-state approaches are useful for an overall understanding of envelope performance, comparing insulation levels, or evaluating simple energy-saving measures. However, they cannot capture phenomena like thermal lag, damping of temperature swings, or correlations between their performance and adverse weather effects or peak loads. That is the key advantage of a building energy model, the BEM. It can characterize materials in a dynamic fashion. By correctly introducing detailed properties of the material in the energy model and stressing it under a given boundary condition, BEMs can represent the changes in thermal behavior that the material or construction have over time. Furthermore, it can correlate those changes in response to the variability of the environment and different building internal conditions. Instead of assuming a steady-state performance, BEM's dynamic modeling captures transient heat transfer, how and when materials absorb, store, and release heat throughout different thermal conditions, weather patterns and particular events. The BEM capability of simulating real-time interactions between material layers, the building envelope, and fluctuating weather or occupancy patterns, expands our understanding of how the material behaves as it interacts with its surroundings. A dynamic, time series evaluation of the material characteristics can display the shifts in its behavior in a daily basis. Furthermore, it provides information about the thermal and energy performance of the material under different seasonal conditions, which helps to visualize the different impacts that a given intervention or solution has in the building's behavior under both summer and winter conditions. This leads to better sizing and design, more accurate predictions of heating and cooling loads, indoor temperatures, and energy consumption, critical for design optimization, evaluation of retrofit solutions, and performance-based decision-making. In regard to material characterization inside the simulated environment, the BEM can calculate the construction's U-value, also known as thermal transmittance, for each construction described in the building. The U-value measures how much heat flows through a building element, such as a wall, roof, floor, or window, per unit area for every degree of temperature difference between indoors and outdoors. Generally speaking, a lower U-value indicates better insulation, while a higher U-value means the assembly allows heat to pass through more easily. Thermal transmittance is expressed in watts per meter Kelvin squared, and the BEM can display its calculated value either by taking into account the convection effects of surface air films on its exterior and interior surfaces, or just focusing on the transmittance of the construction's material layers. Additionally, the BEM can calculate specific outputs that are related to surface heat transfer at each time step of the simulation. These outputs are organized around the inside and outside face of each construction surface and provide additional information on the behavior of the construction. For example, the surface inside and outside face temperatures, which describe the temperature of the surfaces inside and outside face respectively, in degrees Celsius. Regarding heat transfer, outputs like the surface inside face conduction heat transfer rate describes heat flow by conduction right at the inside face of an opaque construction. Here, it is important to note the sign convention, where a positive value means that the heat conduction is pointing towards the inside face, while a negative value means that the heat conduction is directed into the core of the heat transfer surface. Likewise, its outside counterpart describe heat flow by conduction right at the outside face of the construction. Once more, the sign convention indicates that a positive value means that the conduction is towards the outside face. A negative value means that the conduction is directed into the core of the heat transfer surface. When averaged, the combination of the inside face conduction and outside face conduction help to describe the conduction situation in the construction in a nominal way. Here, the sign convention for the outside face is switched to match the inside face. Therefore, positive values indicate heat flowing into the thermal zone. On the other hand, the difference between these outside and inside face outputs can display the surface heat storage rate. This output describes the thermal storage situation of the construction, using a sign convention that is positive whenever heat flows into the construction's core. Other surface outputs are located in Energy Plus documentation, but some notable examples are Surface conduction heat transfer rate, expressed in watts. Surface beam solar radiation heat gain rate, expressed in watts. Surface convection heat gain energy, expressed in joules. Surface solar radiation heat gain rate, expressed in watts. Surface window transmitted solar radiation energy, expressed in joules. Surface window heat gain loss energy, expressed in joules. Finally, the use of the BEM can provide insights into the expected impacts of modifying, sizing, or optimizing any layer inside the construction. The effects of different materials can be further characterized by analyzing the resulting radiant and operating temperatures of the affected building, the shift of its heating days value, compliance with comfort temperatures, or even assessing the change on heating demand and energy consumption for the building. As we conclude this module, let's recap the key insights on the role of material characterization in building energy modeling. The first point is that accurate material data is essential. A BEM can only produce reliable results when the thermal properties of each layer are defined with precision, because even small inconsistencies can influence predicted loads, temperatures, and overall performance. Second, constructions behave as the combined effect of all their material layers. Each layer contributes differently to heat transfer, and it is the interaction between these properties that determines how the envelope performs. Consistent material inputs, therefore, translate into trustworthy construction-level outcomes. Third, BEM allows us to understand both steady-state and dynamic behavior. While steady-state views offer quick comparisons, dynamic simulation reveals how materials store and release heat, how they respond to changing weather conditions, and how these effects shape comfort and energy use across time. We also highlighted those advanced layers, such as air gaps, glazing systems, infrared transparent elements, and phase change materials, require careful modeling. Because they behave differently from conventional materials, their impact can only be captured accurately when introduced properly into the simulation environment. Finally, high-quality material data reduces errors in load estimation and system sizing and allows BEM to serve as a safe virtual testing ground for exploring design options, product improvements, and retrofit strategies before any physical intervention is made. Altogether, these ideas reinforce a simple message. Precise material characterization is the foundation of credible simulation and a key enabler of informed, performance-based decision-making in construction management. Before we conclude, I would like to acknowledge the organizations whose intellectual property supports the tools referenced in this module: the U.S. Department of Energy for EnergyPlus, Lawrence Berkeley National Laboratory for Therm, Design Builder Software for the Design Builder Platform, Affinovatic for CE3X, and ASHRAE for its regulatory and theoretical guidance. Thank you for your participation. I invite you to continue your learning in the next course. Welcome, everyone. Today we begin from BIM to BEM, a practical introduction, a session designed to clarify two essential digital representations used in modern construction and energy performance analysis, BIM and BEM. Even if you have no background in modeling, this course will give you a clear and accessible understanding of what these models represent, how they differ, and how they interoperate throughout a building project. Our goal is simple: to help you understand how these digital tools support better, more informed decisions in sustainable building design. Since BIM, BEM interoperability is still an emerging subject in the industry, we anchor today's session in a structured reference, the study by Geiser-Diener et al., 2024. The article provides a solid conceptual basis for explaining how these models interact. After this slide, we will approach the topic using general theory and practical examples, without further referencing the publication. To understand the relevance of BIM-BEM interoperability, we need to look at the broader context. First, buildings account for a large share of global energy consumption and carbon emissions, which means performance considerations can no longer be optional, they are essential. Interoperability allows BIM and BEM to share information in a coherent and consistent manner, providing teams with earlier access to meaningful performance insights. This connection helps designers evaluate energy behavior with greater accuracy and supports more informed decisions throughout the project's development. In short, interoperability is what allows design intent and energy performance to work together instead of functioning as separate processes. Now, let's begin by defining BIM, which stands for Building Information Modeling. BIM refers to a digital representation of the physical building, but it is much more than a 3D drawing. It is a structured environment where geometry, information, and construction logic are integrated into a single, coordinated model. In a BIM environment, every building component is represented as a 3D element enriched with data. Walls, floors, roofs, columns, beams, doors, and windows are not just shapes. They carry information about materials, dimensions, performance characteristics, and even assembly relationships. This means the model understands how components are built, how they connect to each other, and how they behave as part of the overall system. Because of this embedded intelligence, BIM becomes a platform where multiple disciplines can collaborate effectively. Architects, structural engineers, and MEP designers work within the same model, sharing a common data environment. This coordination supports essential processes such as documentation, quantity takeoffs, clash detection, and consistency checks across drawings and disciplines. One of the key strengths of BIM is that it helps ensure that the project remains coherent from early design stages all the way through construction. For example, when a designer modifies a wall thickness or changes the position of an opening, the model automatically updates related elements, drawings, and schedules. This reduces errors, improves coordination, and supports informed decision-making throughout the project lifecycle. In essence, BIM defines what the building is. It combines accurate geometry with rich, embedded information to create a model that is both precise and constructible. By providing a single source of truth for project data, BIM enhances communication, reduces uncertainty, and lays the foundation for more efficient and integrated design and construction processes. Now, let's take a moment to define BEM, which stands for Building Energy Modeling. While BIM focuses on the geometric and construction detail of a project, BEM provides an analytical representation of how a building behaves from an energy and comfort perspective. In practice, BEM starts by simplifying the building geometry. Instead of modeling every construction detail, it creates a set of analytical surfaces that represent the main paths of heat transfer. Walls, roofs, floors, windows, and shading elements. These surfaces allow the model to track how heat enters, leaves, or moves within the building envelope. Next, the software groups interior spaces into thermal zones. A thermal zone is an area with similar patterns of use, conditioning, and occupancy. For example, offices, meeting rooms, corridors, or storage areas usually become separate zones. This zoning is essential because each area may have different schedules, internal gains, ventilation needs, or temperature set points. BEM then combines all this geometric and zoning information with material properties, local climate data, and vac system characteristics. With these inputs, the model simulates heating and cooling loads, energy demand, equipment performance, and even indoor comfort metrics, such as operative temperature or thermal neutrality. An important point is that BEM is not a construction model. It does not describe how the building is put together. Instead, it tells us how the building performs under different operating conditions. This shift, from how it is built to how it behaves, is what makes BEM a fundamental tool for energy-efficient design, performance optimization, and compliance with sustainability standards. In short, BEM gives us a forward-looking view of building performance, helping designers make informed decisions long before construction begins. To understand the structure of a BIM model, it is important to emphasize that BIM works entirely with three-dimensional elements that represent how the building is physically constructed. Walls, slabs, roofs, and partitions are modeled with their actual material depth. Each component has real thickness and spatial presence inside the model. All geometry is controlled through reference axes, which ensure precise alignment among architectural, structural, and MEP systems. This allows BIM to reproduce the true spatial relationships of the building and support accurate coordination. Another shared characteristic between BIM and BEM is that both models store data in each element. What makes BIM distinct is that its data is multidisciplinary, supporting architecture, structure, building services, quantities, and documentation. In summary, BIM is a volumetric 3D environment that represents the building as a constructible system, complete with real dimensions and data relevant to many disciplines. Unlike BIM's volumetric structure, a BEM model is built from two-dimensional analytical surfaces. These surfaces represent the boundaries where thermal exchanges occur: exterior walls, glazing, roofs, ground floors, and internal partitions. Although BEM does not display the physical thickness of materials, each surface contains parametric material layers that describe thermal behavior, including conductivity, density, and heat capacity. These layers affect the simulation mathematically even if they are not shown as 3D elements. Just as in BIM, every element in a BEM model stores data, but the type of data is very different. BEM focuses exclusively on hygrothermal and energy-related information, the properties needed to calculate heat flow, loads, and comfort. Spaces are not modeled as architectural rooms, but as thermal zones, grouped according to conditioning patterns and internal gains. In summary, BEM is an analytical, simulation-oriented model made of 2D surfaces enriched with parametric thermal properties, designed specifically to evaluate the building's energy behavior. In this slide, we focus on the data categories that BIM and BEM share, even though they use them very differently. Both environments rely on geometry, materials, systems, and environmental context to describe a building. In BIM, geometry is expressed through detailed 3D representations that show real element boundaries and spatial relationships. In BEM, that same concept becomes simplified analytical boundaries that describe where heat transfer occurs. Both also depend on material information, though in different forms. BIM may include physical attributes, such as density or conductivity, when these values are defined. BEM requires parametric thermal properties, because these directly determine energy performance. When it comes to systems, BIM handles structural elements, MEP components, and schedules used for coordination. BEM focuses on HVAC systems, internal gains, and operational profiles, because these variables influence thermal loads. Finally, both models incorporate environmental data, but BIM uses general project information, while BEM works with hourly climatic files to support simulation. The key idea here is that BIM and BEM rely on similar categories of data, but they apply them with very different levels of abstraction and for very different purposes. This slide explains how BIM and BEM use their data once it is inside each model, which is a different question from how that data is structured. In BIM, the purpose of the data is to support design coordination and ensure that the building can be constructed accurately. The information helps different disciplines align their work, confirm system integration, and document the project for construction. Material data supports specifications and quantities, and system data ensures that architecture, structure, and MEP components work together. Environmental inputs mainly provide orientation and context. In BEM, the same data categories serve an entirely different purpose. Here, material information is used to calculate heat transfer. System data helps model vac efficiency, internal gains, and occupancy patterns, and environmental data becomes detailed hourly climate information for simulation. The objective is to predict energy performance, identify loads, and evaluate comfort conditions. The core message is that BIM and BEM rely on comparable datasets, but they use them to answer different questions. BIM supports how the building will be designed and built, while BEM predicts how the building will behave and perform. Understanding this difference is essential for preparing clean and efficient data exchanges between both environments. Materials are one of the most influential elements in both BIM and BEM, because they determine not only how the building is physically constructed, but also how it behaves thermally. In BIM, materials describe the physical composition of walls, floors, and roofs. They define the sequence of layers, the thickness of each component, and the role they play in the assembly. In BEM, materials determine the building's thermal response. They influence how quickly heat travels through the envelope, how much energy is required to maintain stable indoor temperatures, and how the building performs in real conditions. These insights become even more valuable when supported by material testing, prototype fabrication, and laboratory characterization. Through these activities, we obtain accurate values for thermal conductivity, density, heat capacity, and other relevant parameters. This ensures that both the BIM model and the BEM model are based on validated information, not assumptions. When accurate material data is introduced into the digital workflow, the performance predictions become much more reliable. Designers can understand the behavior of new materials, compare alternatives, and make informed decisions early in the project. For a non-modeling audience, the essential idea is that materials are not just visual elements in a model. They are performance drivers, and their accuracy directly affects the quality of both design decisions and energy analysis. In BIM environments like Revit and ArchiCAD, every building element is built from physical construction layers. These layers describe how walls, floors, and roofs are assembled in the real world. To define them correctly, the software requires three fundamental inputs: geometry, thickness, and layer order inside the assembly. This information determines how the element appears visually, how it is quantified in schedules, and how it interacts with other components in the model. Even at a basic level, BIM needs these geometric definitions to ensure that the digital building is a faithful representation of the physical construction system. For a non-modeling audience, the key idea is that BIM represents materials as real, measurable layers, forming assemblies that mirror how the building is actually built. Beyond geometry, BIM platforms allow materials to carry additional attributes that describe their physical and thermal behavior. In Revit, these values are organized as material assets, and in ArchiCAD as building materials. Fields can include density, thermal conductivity, and specific heat capacity. While these inputs are optional for standard design documentation, including them enriches the model and improves its usefulness for performance-related workflows. With accurate data, preferably obtained from testing or verified product specifications, the BIM model becomes a more reliable foundation for later analysis. The important point is that BIM can hold both physical identity and performance information, making it possible to support energy analysis more effectively. In energy modeling tools such as EnergyPlus and Design Builder, materials are represented as analytical layers defined through numerical performance properties. Four inputs are essential: thermal conductivity lambda, which controls heat transfer; density rho, which influences thermal mass; specific heat capacity CP, which determines heat storage; and thickness, necessary for calculating total resistance. These parameters do not need visual detail, they simply need to be accurate. They form the foundation of all heat transfer calculations in BEM tools. With these values in place, the simulation engine can estimate heating and cooling loads and understand how the building envelope behaves. For beginners, the key message is that BEM requires performance data, not physical geometry. Beyond the core thermal properties, BEM tools can incorporate advanced parameters to refine the simulation. These include solar absorptance, thermal absorptance, surface emissivity, and in some cases, moisture-related coefficients. These values help capture how the material interacts with radiation and temperature changes. Energy Plus structures this information through specific material objects, such as material and material. No mass, allowing users to define physical or non-mass layers depending on the construction system. Design Builder provides a more visual interface, but relies on the same Energy Plus definitions internally. The accuracy of these advanced inputs can significantly improve the realism of the model, especially for facade materials or elements exposed to solar radiation. The essential idea is that BEM improves as more validated performance data is included. The performance of a material depends on many different attributes, but here we focus on the properties that can be defined consistently in both BIM and BEM, and that are directly used in the main energy calculations. While each platform can handle additional information, these represent the minimum required parameters for a reliable and interoperable performance model. The first is thermal conductivity, lambda, which describes how easily heat flows through a material. Because it governs heat transfer, it is essential for evaluating insulation and envelope performance. We then consider density, ρ, and specific heat capacity, Cp. Together, these define the thermal mass, the material's ability to store and release heat. Higher thermal mass helps moderate indoor temperatures and can reduce heating and cooling demands. Thickness is also critical. Even materials with moderate inherent performance can behave effectively when used at the appropriate thickness, since this value strongly influences the overall thermal resistance of the building element. In some cases, we may also account for moisture-related behavior, such as vapor diffusion resistance or moisture content. These parameters become relevant in advanced analyses, or when using materials sensitive to humidity. These properties typically come from laboratory measurements, prototype testing, or material sampling, ensuring accuracy in both modeling environments. Understanding this shared set of parameters clarifies how materials influence comfort, energy performance, and the quality of digital simulations, and highlights why having consistent, interoperable material data across BIM and BEM is essential for trustworthy results. Detailed material characterization provides significant benefits across both design workflows and performance assessment. When materials include accurate physical and thermal properties, the analytical model can represent the building envelope much more realistically. This leads to higher thermal accuracy and more reliable simulations. One major advantage is the improvement in predictive performance. With precise thermal conductivity, density, heat capacity, and thickness values, the energy model can better estimate heating and cooling loads, temperature stability, and overall energy demand. This reduces uncertainty and increases confidence in the simulation results. Another key benefit is related to certifications and regulatory compliance. Many sustainability frameworks and energy performance standards require documentation that reflects realistic building conditions. Using well-characterized materials ensures that the digital model aligns with what will actually be built, supporting more credible submissions for certifications, audits, and regulatory approvals. Equally important is the impact on decision-making. When materials are defined with measured properties, both BIM and BEM environments produce results that reflect the true behavior of the digital building, rather than an approximation. This ensures that design choices, such as selecting insulation strategies or evaluating facade systems, are based on scenarios representing the building's actual performance potential. Finally, detailed material characterization strengthens the BIM/BEM integration. With consistent inputs, both models describe the building using the same underlying assumptions, creating a more coherent and reliable workflow. In summary, accurate material data ensures that every study, comparison, or decision derived from the digital model is grounded in a realistic and trustworthy representation of the building. As we conclude this introductory course, it is useful to step back and reflect on what links all the concepts we have explored. Whether we work with BIM or BEM, the underlying purpose is the same: to create a digital representation that captures the essence of the real building, its construction, its behavior, and its performance. We have seen that BIM provides the physical structure of the project, the geometry, the layers, and the assemblies that define how the building is put together. BEM, on the other hand, focuses on the analytical behavior of that structure, evaluating how heat moves, how spaces respond to climate, and how much energy is required to keep occupants comfortable. Throughout this process, materials play a central role. The quality of the information we assign to them determines the reliability of the entire digital workflow. When materials include accurate physical and thermal data, supported by testing, documentation, or verified specifications, the building models we produce become much more than illustrations. They become decision-making tools. This is ultimately the value of connecting BIM and BEM concepts, ensuring that every study, every prediction, and every design choice is based on a model that represents the real performance potential of the building, not an abstraction. The more carefully we define the data behind the model, the more confident we can be in the outcomes it supports. Understanding these principles strengthens our ability to design better buildings, evaluate them more responsibly, and use digital tools in a way that truly reflects the real world they represent. Before we finish, I want to acknowledge the organizations whose technical resources supported the development of this course. We thank Graphisoft and Autodesk for their documentation on BIM environments, Design Builder for its contributions to practical energy modeling workflows, and the U.S. Department of Energy for providing the foundational technical references behind EnergyPlus. Their work has helped establish the standards and methods that make today's BIM and BEM practices possible. If you are interested in continuing your learning path, I invite you to join the next course.
Welcome, and thank you for joining this training session. In this course, we will take a practical look at the software ecosystem used to create building energy models and understand how different tools contribute to the modeling workflow. Our goal is to provide you with a clear overview of the main simulation engines, graphical interfaces, and analysis tools that support building performance evaluation. From simplified compliance-oriented applications to advanced dynamic simulation environments. We will also explore how internal BIM energy tools, such as Revit Insight and ArchiCAD ECO Star, extract information directly from the model to generate fast, early-stage performance insights. This introduction will give you a solid foundation to understand where each tool fits, how they interact, and how they support reliable, data-driven energy modeling. Let's begin. In the following training course, we will introduce learners to widely used platforms and tools for energy modeling, as well as briefly explain the typical workflow in using these tools to generate a building energy model. A building energy model generation is constrained by the model's objectives and its final use. It is a broad subject that requires expertise and keen attention to detail. It usually demands from the BEM developer knowledge and skills in different fields, as well as, in various kinds of software tools that help to define various of the BEM's components. The following course will briefly list some of these software tools along their purpose to give a broad view of the BEM software ecosystem. The first step is to define the simulation environment for the model. In other words, the simulation engine used to perform the BEM's calculations. Depending on the complexity of the model and its required scope, there are various options to choose from. Some focus on the generation of simplified models, usually used as quick assessment tools in certification and code compliance. For example, CE3X, which is a simplified building energy modeling and assessment tool that can evaluate and rate energy performance. It is designed to make energy certification faster and easier for technicians without requiring full dynamic simulation. HULC, a building energy performance tool that performs a quasi-hourly dynamic simulation, evaluating how the building behaves under standard climate files and usage conditions. It is a software designed specifically for verifying energy compliance with the Spanish Energy Performance Standard. Other engines offer a more in-depth approach for detailed thermal modeling, with large libraries of constructions, HVAC systems, schedules, and loads. These simulation environments are capable to model complex systems and calculate the energy performance and indoor environmental conditions of buildings under different design or operation scenarios. Thus, they are widely used for code compliance, energy audits, retrofit analysis, and research. For example, Apache Sim, a dynamic thermal simulation engine inside the Integrated Environmental Solutions and Virtual Environment (IESV) software suite. It is a powerful, building energy modeling tool that aims to assess the sustainability of a building from both an energy and carbon usage viewpoint. TRNSYS, a modular, component-based simulation environment designed to model complex energy systems. It uses an engine called the kernel, which allows to simulate the behavior of transient systems, assessing the behavior of thermal and electrical systems, as well as modeling traffic flow and biological processes. Modelica, not a single engine but a non-proprietary, object-oriented modeling language used to describe complex multiphysics systems, like thermal, electrical, mechanical, or control systems. It provides an equation-based modeling of the building for digital twins and advanced control development. Finally, Energy Plus, a whole building energy simulation engine developed by the U.S. Department of Energy. It is a free, open-source, and cross-platform simulation engine that is capable of modeling the heating, cooling, lighting, ventilation, and other energy flows in buildings. Energy Plus is a powerful physics-based engine with detailed thermal modeling that allows for dynamic simulation at sub-hourly time steps and for the simultaneous solution of indoor conditions and HVAC system response. Its simulation engine can provide numerous results regarding ambient and surface temperatures, thermal and energy behavior, radiative and convective effects, thermal mass, among others. Which is the reason why Energy Plus is widely used to simulate the energy performance and indoor environmental conditions of buildings under different design or operation scenarios for design, audit, and research purposes. There are multiple programs and tools that shape the software ecosystem around Energy Plus simulation environment. Regarding the generation of the model's geometry, its location, orientation, as well as its architecture, materials, and different active systems, these parameters can be introduced directly into Energy Plus, which is a highly time-consuming process, or by either the importation of a GBXML file provided by a BEM model, or by the use of different graphical interfaces. Some of the most well-known graphical interfaces that simplify the process of generating the BEM are Open Studio, which is an open-source graphical interface for BEM generation inside Trimble SketchUp software, that provides a user-friendly framework to work with Energy Plus and Radiance. SiteTherm E Plus is part of CYPE Suite, and its function is to perform energy modeling and simulation of buildings with Energy Plus engine. It can import models from BIM sources, CYP architecture module, or defined by the user. Design Builder. A commercial BEM software that provides one of the most intuitive user interfaces for EnergyPlus-based modeling. It is widely used by engineers, architects, and consultants for detailed simulation and compliance. In addition to the generation of the base building energy model, there are multiple tools whose objective is to provide insights into the building, its surroundings, and its components. These tools' objective is to deepen the understanding of a particular system in relation to the building model. For weather analysis and its relationship with the building's passive systems, envelope. Climate Consultant offers an understanding of local climate behavior, identifying envelope strategies and HVAC approaches before modeling. This software is a free climate analysis tool that analyzes raw weather data, providing the user with psychrometric charts, sun charts, wind roses, comfort diagrams, and passive design strategy maps. In relation to material characterization, and the assessment of their performance in a steady state prior to their introduction into the BEM simulation environment, the use of tools like THERM can offer insights into the behavior and performance of a given construction. THERM is a two-dimensional heat transfer simulation tool created by Lawrence Berkeley National Laboratory, that calculates linear transmittance, thermal bridges, and localized heat flow patterns within a given construction. It is used for detailed modeling of thermal bridges and facade attachments, evaluating U-values of complex sections, and identifying condensation risks and surface temperatures. Equally important is the correct assessment of glazing properties that will be introduced into the building energy model. Here, Window, also developed by Lawrence Berkeley National Laboratory, is a tool that evaluates optical, thermal, and solar properties of glazing and window assemblies. It can help characterize multi-layer windows, generating both average and spectral values for transmittance, visual and solar performances, and emissivity metrics. Together these tools offer valuable support in the introduction of material properties into the building model. It is important to note that BEM development often requires the study and analysis of large sets of data to describe the building's boundary conditions and to assess its thermal and energy performance. In essence, the use of programming languages like Python, RStudio, and MATLAB, in conjunction with spreadsheets like Excel, are woven into the development of the model itself. These languages can be used to generate subroutines that provide statistical analysis of measurements, definitions of stresses and loading scenarios, as well as the assessment simulated results. Furthermore, programming languages like Python and MATLAB can be employed to generate and train black box building energy models that use reinforced learning, LSTM neural networks, or others, and that can even operate alongside the building's management system. These programming languages can also be used in the calibration of white box models. As a matter of fact, there are multiple tools, plugins, and strategies that can operate with Energy Plus to perform the calibration of its parameters. For example, GPlus is a parametric simulation manager that allows its users to define parameter ranges and combinations and then run large numbers of Energy Plus simulations. An advantage that is then expanded in JE++EA, which integrates an evolutionary algorithm to perform multi-objective optimization of parameter values. Together, these tools allow to develop high-fidelity models that reflect climate variations, material properties, internal stresses, thermal loads, schedules, and system interactions with increasing accuracy. No single tool can address all modeling needs. Therefore, the BEM software ecosystem forms an integrated and complementary toolkit that supports the entire generation of building energy models and its analysis, each contributing a layer of precision, insight, or functionality. Understanding how internal BIM energy analysis tools work is essential for evaluating building performance early in the design process. These tools are fully integrated within BIM platforms to provide fast, early-stage insights. They automatically read the building geometry, construction layers, and material properties from the BIM model, and use this information to generate a simplified energy model composed of thermal zones and analytical surfaces. Once the model is created, the system applies predefined calculation methods to estimate heating and cooling loads, overall energy demand, solar gains, ventilation effects, and other key performance indicators. The aim is not to produce a fully detailed engineering simulation, but to offer accessible feedback that informs early design decisions efficiently. For material developers, this workflow is particularly valuable. It establishes a direct link between material properties and measurable building performance, allowing teams to test scenarios, compare materials, and demonstrate their impact without needing deep simulation expertise. With this foundation in place, we can now explore specific BIM-integrated tools that leverage these capabilities, such as Revit Insight and ArchiCAD ECOStar, which provide designers with actionable energy insights directly within their modeling environment. Revit Insight is Autodesk's internal tool for early-stage energy analysis. It extracts geometry and basic material information directly from the BIM model and generates an energy model automatically. One of its strongest advantages is speed. It allows users to compare different design options and observe how insulation, glazing type, orientation, infiltration, or shading affect overall building performance. Insight focuses on sensitivity-based results rather than exact engineering precision. This makes it excellent for exploring trends and highlighting which parameters have the biggest influence on energy use. For material developers, Insight becomes a powerful communication tool. You can quickly demonstrate how your innovative material performs compared to traditional alternatives, using visual outputs that are easy for clients, architects, and stakeholders to understand. ArchiCAD's ECOStar provides a more physically detailed approach to energy evaluation. It reads geometry and material definitions from the BIM model, but allows deeper customization of construction layers, thermal mass, optical properties, and HVAC parameters. ECOStar produces quantitative results such as monthly heating and cooling loads, energy balances, internal gains, and comfort evaluations. This makes it especially suitable for innovative materials where thermal mass, reflectivity, emissivity, or phase change behavior are important. Because ECOStar relies so strongly on the physical accuracy of the material definitions, well-characterized materials produce clearer, more reliable outcomes. For material developers, this can significantly support technical validation and strengthen the credibility of performance claims. Although Insight and ECOStar are both internal BIM simulation tools, their strengths differ. Insight is optimized for rapid feedback. It is highly visual and ideal for exploring alternatives early in the process. Its sensitivity graphs provide a clear picture of how design choices influence overall performance. ECOStar is more suited to detailed analysis. It offers more control over construction layers, material properties, and thermal behavior. As a result, it produces more quantitative and physically grounded outcomes. You can think of it like this: Insight gives trends and relative influence, ECOStar gives more detailed, measurable results. Both serve important roles depending on the stage of design and the level of confidence required. One of the most important aspects for material developers is understanding which material properties these internal BIM simulation tools actually use. Both Revit Insight and ArchiCAD ECOStar rely on a small set of essential thermal and optical parameters to estimate how materials influence building performance. For opaque components, such as walls, roofs, and floors, the tools use thermal conductivity, density, and specific heat capacity to model heat transfer and thermal mass. Layer thickness and the position of the material within the assembly are equally important because they determine the overall thermal resistance and how mass or insulation contributes to performance. Surface properties such as solar absorptance or reflectance influence how much heat the envelope absorbs from sunlight. For glazing systems, the tools require properties like U-value, solar heat gain coefficient, and visible transmittance. The composition and thickness of the panes also matter, especially when evaluating advanced glazing or coatings. These tools do not require complex laboratory datasets, but they do depend on accurate physical values. Well-defined material inputs ensure that simulations reflect the actual behavior of your product, making performance comparisons clearer and more trustworthy. These internal BEM simulation tools provide a set of results that are especially valuable for evaluating materials. Energy demand results help quantify how much a new insulation or facade material reduces heating and cooling needs. Peak load reduction results show how materials help downsize HVAC systems. Solar gain influence is particularly important for glazing and surface coatings. Comfort indicators offer insight into how materials impact indoor environments. Sensitivity graphs provide a powerful way to highlight how much a specific material contributes to overall performance relative to other factors. Together, these outputs form a strong foundation for comparing new materials to traditional ones and for communicating value to architects, engineers, and end users. To conclude, internal BIM energy tools like Revit Insight and EcoStar provide a valuable bridge between material characteristics and building performance. They make early-stage evaluation fast, accessible, and understandable, even for users without specialized modeling experience. For developers of innovative or sustainable materials, these tools allow you to demonstrate performance advantages, validate assumptions, and communicate your product's value in a real building context. By supplying accurate material data, you enhance the reliability of the results and help accelerate the adoption of high-performance materials in construction projects. As we wrap up this session, I would like to acknowledge the organizations whose intellectual property and technical contributions supported the software and methods referenced throughout this course. We thank the U.S. Department of Energy for the development of Energy Plus, and Lawrence Berkeley National Laboratory for the Therm simulation tool. We also recognize Design Builder software for the Design Builder platform, and F-Innovatic for the CE3X application. In addition, we acknowledge Autodesk for the Insight Energy Analysis environment integrated in Revit, and Graphisoft for the EcoStar Energy Evaluation System within ArchiCAD. Finally, we thank ASHRAE for the regulations, standards, and theoretical guidance that informed many of the concepts discussed. Your participation is greatly appreciated, and I encourage you to stay engaged as we continue exploring new topics in the upcoming course. Welcome, and thank you for joining Module 2.2.5 on Energy Performance Simulations and Analysis. In this session, we will explore how energy models evolve from theoretical representations into calibrated tools that reflect real building behavior. You will see how measurements, data streams, and simulation methods come together to reduce the performance gap and support more accurate decision-making. I'm glad to have you here, and I look forward to guiding you through this module. In the following training course, we will address the following objectives. 1. Explain the principles behind the calibration of building energy models. 2. Identify key factors that intervene in BEM development. 3. List some of the benefits of using calibrated BEMs for energy performance analysis and results. As such, this course examines the reasons behind building energy model calibration, its advantages and requirements. The main objective behind BEM calibration is to ensure that the model's results accurately reflect how the building performs and therefore emulates the building's actual operating behavior in a non-intrusive simulation environment. It is important that the generated BEM is as detailed as possible in order to capture the nuances of real building behavior. This is performed by accurately representing in the simulation environment the building's architecture, its geometry, materials and constructions, schedules, loads, and HVAC system. However, it is important to note that the level of detail and depth of the model is constrained by project requirements and the final purpose of the BEM, whether it will be used for retrofit evaluation, operational optimization, measurement and verification, M&V, fault detection diagnosis, or compliance. The term calibration or training depends on the type of the model. If it is physics-based white box model, we calibrate its parameter values. On the other hand, if it is a data-driven black box one, we train the model. In both cases, the process attempts to align the simulated predictions with measured data, such as energy consumption, heating demand, and indoor temperatures, so that the BEM can faithfully represent the actual building. The importance of this calibration process lies in reducing the energy performance gap, the difference between predicted and actual performance. By constraining the model to known external and internal conditions, stresses, and occupant patterns, the calibration process modifies certain key parameter values to minimize the difference between simulation results and reality. This seemingly simple process is actually a significant challenge. The energy balance of a building and the interaction of its HVAC systems represents a complex problem filled with uncertainties. Various factors that contribute to the generation of thermal comfort and energy demands are related to variables of an indeterminate nature. Therefore, attempting to solve the system of nonlinear equations that defines the building's energy balance requires the introduction of assumptions and the estimation of certain key parameters in order to accurately simulate the building's real behavior. The principle behind the calibration process aims to provide a correct resolution of the building's energy balance by modifying the values of different key parameters that form part of the building systems while satisfying interior conditions like indoor temperature and energy demand simultaneously and at the same level of resolution. In other words, calibration is an iterative process that benchmarks BEM solution at multiple levels that define the behavior of the building system, for example indoor climate, temperatures, and energy demand, consumption, while maintaining the BEM's result resolution across all levels. This process is performed until the calibrated BEM yields a solution that closely matches real-world behavior. To achieve this match, the model must meet the energy performance conditions that are established by international standards like the International Performance Measurement and Verification Protocol, IPMVP, or the American Society of Heating, Refrigerating and Air Conditioning Engineers, ASHRAE, Guidelines 14. At the same time, the model must meet the indoor performance conditions for temperature established by international standards like the Chartered Institution of Building Service Engineers (CIBS, TM63). Meeting these criteria enables confident use of the model for future use in forecasting energy savings, improving building operation, and validating interventions. In essence, calibration transforms a BEM from a theoretical approximation into a reliable decision-making tool rooted in measurable reality. Today's BEM's development combines physics-based modeling with data-driven insights from a variety of sensors, IoT platforms, and management systems to increase the robustness of the model. The current training course delves into graybox models that can couple thermal behavior, occupant shifts, and weather patterns with real-time data streams. Their development requires expertise, accurate and organized management of raw data, and careful attention to detail, especially as the model's complexity increases. Sometimes, even state-of-the-art BEMs can have trouble predicting real-world performance. Poorly defined inputs, incomplete documentation, or uncertainties in operational factors can prevent the model from reaching the threshold set by the standards and produce a partially calibrated BEM. In this regard, it is important to note that the calibration process objective is to minimize the gap between simulation and reality, correcting the model's behavior, and therefore it always aims to improve the simulation results. The calibration methodology shown in this course is derived from a data-driven physics-based model and has three main branches or pipelines that intervene in the process, each observing one of the main principles that governs building energy models, and each playing a key role in the improvement of accuracy of the BEM. In the first place, the information pipeline, which is focused on the development of the physics-based energy model itself and takes into account all the related documentation available to define the building and its passive and active systems, including the introduction of material parameter values. Its objective is to generate a model that closely represents reality, one of the biggest challenges since it requires to align the BEM's complexity with the project needs. In this regard, the information used in the simulation environment must be categorized based on its quality source and value, and then introduced in the simulation environment in an organized fashion, so that better quality data overwrites lower quality data. One option to do this is to follow the guidelines of Young and Becerrich-Gerber, which grades the information obtained from measuring campaigns as best quality. The next best data source is obtained from site surveys or laboratory conditions, following with information obtained from building documentation, where energy performance reports take preference to operation and maintenance manuals, and these in turn are preferable to as-built documents. The next level is assigned to design documentation, followed by building codes and standards, and then manufacturers' handbooks. The lowest level of quality for information belongs to default settings, and finally assumptions made by experience. By applying these criteria when defining the model's parameters, the base energy model generated becomes a mesh of information from different quality degrees that is aimed at representing as accurately as possible the building's real conditions. The second pipeline is dedicated to data analysis for the building. The key aspect of this pipeline lies in the data management plan and its application. First, it is here that the project requirements define the grain of resolution of the data obtained, for example, 10 or 15-minute data stream, hourly data, or other. Afterwards, the data management plan setups and applies the project standard that governs the health of the data stream. In other words, what defines a missing or error value, how these errors are found and flagged, and what is the treatment given to both missing and wrong data. This branch's objective is to evaluate and check the data stream provided by the monitorization of either the building management systems or any additional sensors deployed inside the structure, and generate a healthy stream of data that can be further characterized as 1. Input data, providing the model with a stream of values that are used to define external stresses, for instance weather files, or define the building system's boundary conditions, as set points, load profiles, or other. 2. Control data, where the measurements obtained are solely used to compare the simulation results against real performance, for example the building's energy consumption or its indoor temperatures. Finally, the simulation pipeline, which deals with the calibration's computational and mathematical processes. It focuses on the modification of parameter values and variables, the establishment of objective functions, and the benchmark of the model's results. Regarding the selection of key parameter values, for most cases it can be performed after the application of a sensitivity analysis. However, the manipulation of certain parameters, like those in HVAC components, can influence the sensitivity of others, which increases the complexity of this process. It is important that the base BEM undergoes an initial result assessment where its functionality and performance are studied prior to the parametrization process. The results from this initial run are indispensable for establishing how the model reacts and selecting the key parameters that will be calibrated. The selected parameters are then optimized based on an objective function. An objective function is a mathematical expression that aims to reduce the gap between simulated results and reality. It can usually be expressed in terms of minimizing residuals or using statistical indexes suggested by international standards. The optimization process takes place by running multiple BEM simulations on tools like JE++ EA software. JE+ is a parametric tool that runs Energy+ models. JE++ EA adds a non-sorting genetic algorithm to JE+ running platform. By generating a series of objective functions, in terms of indoor climate, heating, and energy consumption, the genetic algorithm searches for the parameter values that will produce the best, or optimal, fit between the simulated results and the measurement control data. The solution of the optimization process must satisfy the multi-level benchmark previously stated. Therefore, when the BEM's indoor climate and its energy behavior meets the international standard criteria, it is fully calibrated and thus can be called a digital twin. The importance of calibration lies in generating an accurate model, one whose simulation emulates reality. A building energy model that captures the indoor climate behavior by producing simulated indoor temperatures related to the actual building, while reducing the model's performance gap and demanding similar energy consumption that the building has in reality. This enables confident use of the model for forecasting energy savings, assessing design options, improving building operation, and validating interventions. In essence, calibration improves a BEM into a reliable decision-making tool rooted in measurable reality. For example, when used as a referential model, a calibrated BEM can offer the expected performance of different designs of a given energy-saving measure, for instance the retrofit of the building's envelope. This analysis can be performed on a macro scale, delivering the expected impact of the measure if installed in the building. Or in a more detailed scale, allowing the study of the measure itself and how it would behave in the building under different thermal stresses and conditions. Furthermore, calibrated BEMs can help to establish new energy-saving strategies that aim for the decarbonization of the building sector, including photovoltaic plant, PV, sizing, design, and optimization. For example, a calibrated BEM can be used in the optimization of the consumption of a building's own PV production, self-consumption. Where a demand-side optimization strategy of the building's thermostat and thus, its heating and cooling load, can assess the level of improvement in self-consumption of its PV plant. Additionally, the calibration process itself offers new insights into the building operation and the relationship between its different systems. When deployed alongside the building management system, the calibrated BEM can alert maintenance personnel of faults in the installation and their location. For instance, wrongly closed valves or HVAC component malfunction, prompting corrective measures, and/or predictive maintenance. The methodology presented in this training module, along with selected applications of calibrated building energy models, is discussed in the following open access articles. Links to the corresponding case studies can be found in the course recommended documentation and resources document. As we conclude this module, let's review the main insights behind energy performance simulations and the calibration of building energy models. Calibration is essential because it allows a model to reflect real building behavior rather than theoretical expectations. By aligning predictions with measured data, a calibrated BEM significantly reduces the performance gap and becomes a trustworthy representation of how the building actually operates. A key aspect of this process is the quality of the inputs. The accuracy of geometry, materials, loads, schedules, HVAC systems, and operational data all determine how well the model can match reality. Calibration depends not only on the simulation environment but also on the organization, validation, and treatment of the data used to define boundary conditions and control variables. We also examined how calibration requires evaluating the model at multiple levels, including indoor temperatures and energy consumption. Meeting internationally recognized criteria ensures that the model provides credible insights for future analyses. Furthermore, optimization techniques refine key parameters so that simulated outputs align with real-world performance. This iterative process transforms the BEM from a theoretical approximation into a reliable analytical tool. Once calibrated, the model can support forecasting, evaluate retrofit strategies, improve building operation, identify faults, and guide energy-saving interventions. In essence, a calibrated BEM becomes a powerful decision support system grounded in measurable reality. Before we close, I would like to acknowledge the organizations whose intellectual property supports the tools referenced throughout this module. We thank the U.S. Department of Energy for Energy Plus, Lawrence Berkeley National Laboratory for the Therm Simulation Tool, Design Builder Software for the Design Builder Platform, and FNOVATIC for the CE3X application. We also recognize SHRAE for the regulatory and theoretical frameworks that inform many of the modeling principles used in this course. Thank you for your participation. I invite you to continue your learning in the next module.
Welcome to this session on BIM, BEM interoperability. In the next minutes, we will explore how information moves between these digital environments, and why the consistency of that exchange is essential for achieving reliable energy simulations and accurate performance outcomes. Our focus will be on understanding the data flows, the intermediate formats used in practice, and how each stage of the process affects the way materials are represented once the model enters the analytical domain. You will see where information tends to remain consistent, where it can degrade, and what strategies help protect the integrity of material properties throughout the workflow. This introduction sets the foundation for examining how interoperability influences thermal accuracy, design decisions, and the overall quality of building energy models. Let's begin by recapping the core concepts that connect the digital description of a building with its analytical behavior. Now we shift the discussion to how digital models communicate with each other, and why this matters specifically for construction materials. Today, buildings account for a very large share of global energy consumption and greenhouse gas emissions. Improving performance is no longer optional, it's regulatory, competitive, and reputational. On one side, BIM gives us a rich digital representation of the building, what is built, where, and with which systems and products. On the other side, BEM provides the analytical view, how that building behaves thermally, how much energy it uses, and how different design choices change the result. Interoperability is the bridge between those worlds. If the BIM model cannot pass reliable data to the BEM tools, we lose time, we re-enter data manually, and the energy results may not reflect the real product performance. For material manufacturers and researchers, this is a strategic issue. If your product data does not flow correctly into BEM, it cannot demonstrate its value in design decisions, certifications, or regulations. Interoperability refers to the capacity of BIM and BEM to exchange and interpret information reliably. Both models contain geometry, materials, systems, and environmental data, but they structure this information differently. For an effective exchange, design information must be translated into the analytical logic required by the energy model. This translation involves converting constructible 3D elements into 2D analytical boundaries, reformulating room definitions into meaningful thermal zones, and ensuring that materials include the thermal parameters needed for simulation. Interoperability, therefore, depends on consistency in the BIM model, and on the ability to map its data to the analytical requirements of the BEM environment. Reliable exchange is the foundation for accurate performance evaluation, since the quality of the analytical model depends directly on the quality and clarity of the information received from BIM. A successful exchange between BIM and BEM depends on the quality, structure, and completeness of the information prepared before export. Ensuring geometric alignment is essential so that analytical surfaces connect correctly and no gaps or overlaps occur. Likewise, maintaining closed spatial boundaries allows the analytical engine to generate functional thermal zones that reflect the intended building layout. The model's material definitions must include the necessary thermal attributes, such as conductivity, density, and specific heat, so the simulation tool can calculate heat transfer with precision. In parallel, the system information should be expressed in terms that capture operational behavior rather than construction detail, enabling a realistic representation of FAC performance during the simulation. Finally, the environmental inputs, weather files, schedules, and occupancy profiles, must follow the formats expected by the BEM workflow to avoid inconsistencies. When all these elements are carefully prepared, the analytical model receives clean, coherent, and simulation-ready data, improving both the accuracy and the efficiency of the energy analysis. Most interoperability issues arise during the transition from volumetric construction geometry to analytical surfaces. Misaligned walls or slabs often produce open boundaries, which prevent the formation of correct thermal surfaces. Incomplete room enclosures can generate partial or duplicated thermal zones. When material properties are missing or incomplete, the simulation engine cannot calculate thermal behavior accurately. Overly detailed assemblies also pose challenges, since the analytical model requires simplified surfaces rather than full 3D stratigraphy. In many cases, these issues reflect inconsistencies within the BIM model rather than limitations of the export format. Understanding these common problems helps anticipate where preparation is needed and improves the reliability of the resulting energy model. Before any energy analysis can be performed, the BIM model needs to be structured in a way that allows analytical software to interpret it correctly. This does not require advanced modeling knowledge, but it is important to understand the principles involved. The model must follow clear and consistent geometry, meaning that walls, floors, and openings should align logically so that the energy tool can identify the building's boundaries. For the analytical model to define thermal zones, each space must be enclosed by complete room boundaries, even if those boundaries are simple. Some construction details that are important for documentation are not needed for energy simulation. These elements are often simplified so that the analytical model can focus on what affects performance, surfaces, materials, and thermal connections. Materials also need to include basic thermal attributes, such as conductivity and density, because these allow the energy model to calculate heat transfer. Finally, openings and surfaces must be coherent, meaning that windows, doors, and walls interact cleanly with one another. The goal is not to create a perfect or detailed model, but a consistent and readable representation of the building so the analytical engine can generate accurate results. Before we continue deeper into interoperability workflows, it's helpful to briefly recap the core concepts that connect BIM and BEM. Understanding these foundations makes it clearer why material data plays such a central role in performance modeling. BIM provides a detailed representation of the physical building. It describes the geometry, the configuration of construction assemblies, and ideally the actual materials or products used in each layer. BIM's purpose is primarily organizational and descriptive. It tells us what the building is made of and how its components relate to each other. BEM, in contrast, represents a performance-oriented view of the same building. Instead of focusing on construction detail, it organizes the building into thermal zones, assigns internal loads, applies FAC systems, and evaluates how the structure interacts with weather conditions. BEM cares less about visual detail and more about thermal behavior. What both domains rely on, whether explicitly or implicitly, are materials, constructions, and surfaces. These elements define how heat moves through the building and how accurately simulations represent real behavior. When BIM and BEM describe these elements differently, especially materials, we get misalignment in results. Keeping these ideas in mind will help clarify why material characterization becomes a critical link in any interoperability workflow. Before diving into the specific formats, it is helpful to understand how information typically travels from BIM to BEM. Most workflows rely on an intermediate exchange format that acts as a bridge between the BIM authoring tool and the energy simulation platform. In practice, the two formats used most frequently are IFC and GBXML. Each one was developed with different intentions, which means they handle materials and constructions differently. IFC is widely used because it supports broad coordination across disciplines, while GBXML is more common in energy workflows because it was structured with thermal zones and constructions in mind. At this stage, what matters is not the technical detail of each format, that will be covered next, but the fact that they do not preserve material information equally. Depending on which export path the BIM model takes, the resulting BEM model may retain more or less of the original thermophysical detail. Most workflows eventually produce an IDF file for EnergyPlus, where all material data must be explicit and numerically complete. Understanding that different routes into IDF offer different levels of material fidelity helps manufacturers anticipate where their properties may remain intact and where they may require additional support or guidance. IFC is the most widely adopted open standard for BIM data exchange, and one of its defining characteristics is its ability to support a broad ecosystem of disciplines and software. The same IFC file can be used by tools for structural analysis, cost estimation, construction planning, rendering, facility management, and many others. This versatility is a major strength, but it comes with an important limitation for energy modeling. IFC was not designed as a specialized thermal or simulation schema. Its material and construction entities exist, but their level of thermal specificity is intentionally limited, because IFC must remain compatible with a wide range of applications that do not require detailed energy data. As a result, when a BEM tool reads an IFC file, it must perform a mapping process, translating IFC materials, layer sets and properties into the structures required by the simulation engine. If the BIM authoring tool did not populate those thermal fields, or if the mapping rules are incomplete, the BEM environment may rely on generic or simplified material definitions. This multipurpose nature of IFC is important to understand. It excels in coordination across disciplines, but it does not guarantee complete thermophysical detail, making careful data preparation essential for accurate BIM/BEM interoperability. GBXML is designed specifically for energy modeling, so it aligns naturally with the needs of BEM tools. It represents thermal zones, surfaces, and construction layers, and typically carries key thermophysical values such as thickness, conductivity, density, and specific heat. Because of this focus, GBXML often preserves more material-relevant detail than a general IFC export. Its structure makes it easier for BEM tools to read and interpret thermal assemblies. The trade-off is that GBXML may simplify geometry to match energy modeling conventions. However, for material fidelity, it is usually the more reliable of the two primary export paths. IDF is where all material data becomes numerical and explicit for simulation. For opaque materials, IDF requires values like conductivity, density, specific heat, thickness, and optical thermal absorptance. Because IDF assumes complete inputs, any missing data from the BIM or GBXML export results in default values, which may not represent actual performance. This is why the upstream data structure matters so much. The IDF will only be as accurate as the information it receives. This slide presents a comparative view of IFC, GBXML, and IDF to clarify how each format contributes to the BIM/BEM BEM workflow. The aim here is to understand their differences in structure, purpose and level of detail, rather than revisiting definitions already discussed. Looking at the table, IFC functions as a multipurpose exchange format, compatible with a wide range of disciplines. Because its structure must remain flexible, the amount of energy-relevant material information it carries is variable and often depends on how the BIM model was authored and exported. GBXML occupies a more focused position within energy and VAC analysis, which enables it to represent zones, surfaces, and construction layers with greater consistency. As a result, GBXML tends to preserve core thermophysical properties more reliably than general-purpose formats. At the simulation stage, IDF requires all material definitions to be explicit, fully numerical and complete. Since the simulation engine cannot infer missing values, IDF is the most detailed and the most sensitive format, reflecting any gaps introduced earlier in the workflow. The key takeaway is that all three formats rely on a set of shared physical concepts, yet they differ significantly in how precisely they express them. Understanding these distinctions helps anticipate how material data evolves along the interoperability chain, and where additional structure or validation may be necessary to achieve trustworthy energy results. In the BIM environment, materials are defined as structured data objects attached to physical elements such as walls, slabs, roofs, or glazing systems. Each construction element references a material with attributes such as identity, classification, visual appearance, and a defined position within a layered assembly. When available, these materials may also include thermal fields that can later support analytical workflows. The level of detail captured in BIM materials can vary significantly across projects. In highly coordinated models, materials may include complete physical and thermal definitions, while in others, the focus may be purely graphical or organizational. This variation directly affects downstream workflows. If the fields required for energy modeling are missing, no export format can reconstruct them later. For this reason, datasets provided directly by manufacturers play a crucial role. When materials enter the BIM model with validated thermal properties, standardized naming, and correct layer placement, the entire interoperability chain benefits. These high-quality definitions increase confidence in the data and reduce the risk of substitutions or simplifications during export. Ensuring accuracy at the source is one of the most effective ways to improve BIM to BEM fidelity. Beyond their role in defining assemblies, BIM materials function as verified data sources that support multiple disciplines across the project lifecycle. Because BIM operates within a shared digital environment, material definitions are continually reviewed, referenced, and validated by architects, engineers, planners, and cost consultants. This multidisciplinary exposure strengthens the reliability of the material information. A well-defined BIM material becomes a single point of truth that can be reused across applications, such as cost estimation, specification management, rendering workflows, and building energy modeling (BEM). When these tools rely on a common data source, the consistency of material interpretation increases substantially. For BEM, this consistency is especially valuable. A stable BIM material provides a dependable foundation for layer sequencing, naming conventions, and essential thermal property values, all of which improve the quality of GBXML and IDF outputs. Even when export formats differ, a well-structured BIM definition helps preserve the information required for accurate simulations. This is why structured, validated BIM materials, particularly those supplied directly by manufacturers, can significantly enhance the fidelity, consistency, and credibility of the entire BIM/BEM pipeline. As material data moves from the BIM environment into BEM-compatible formats, certain properties remain stable while others become simplified. The parameters that transfer most consistently are those that simulation engines rely on universally: layer sequencing, thermal conductivity, density, specific heat, and thickness. These properties define the thermal mass and transmittance of an assembly and are recognized across GBXML and IDF with little ambiguity. Other characteristics, however, undergo significant reduction. Behaviors that vary with temperature, humidity, or phase change rarely survive the transition, because standard exchange schemas are not designed to capture dynamic or multiphysics responses. Similarly, advanced optical definitions used for high-performance glazing systems often require manual adjustment, as they exceed what is typically exported from BIM. Metadata such as manufacturer identity, product codes, or certification details also tends to disappear in BEM tools unless added intentionally. These attributes are not required for thermal calculations and therefore are not prioritized in most interoperability workflows. Understanding which properties persist and which diminish helps identify where targeted digital documentation or simplified simulation parameters may be necessary. This ensures that essential characteristics of innovative materials remain visible and meaningful once they enter energy modeling environments. Central material libraries provide a structured way to ensure that material information remains consistent and traceable across the entire digital workflow. Instead of relying on each modeler or simulation specialist to enter properties manually, a shared library establishes one authoritative version of each material, including naming, classification, and physical characteristics. This approach significantly reduces inconsistencies between tools. When BIM and BEM platforms reference the same dataset, the likelihood of mismatched values or contradictory definitions is minimized. For analytical workflows, this consistency is especially important because even small variations in material properties can influence energy results. Another benefit is the ability to align material definitions with industry classification systems or regulatory frameworks. By embedding classification codes, regional standards, or product families directly into the library, teams create a foundation that supports both interoperability and compliance. From a strategic perspective, central libraries elevate the quality of digital information and make it easier for external tools to interpret materials without reprocessing or approximation. When these datasets originate from validated sources, such as product manufacturers, the reliability of the entire BIM to BEM chain increases substantially. For innovative materials, interoperability is not only a technical requirement, but a key factor in demonstrating performance differentiation. When material data is transferred accurately across BIM and BEM, it becomes possible to quantify benefits, such as improved insulation, enhanced thermal mass, or advanced optical behavior in realistic design scenarios. This accurate representation enables research teams and design professionals to evaluate how a new material performs under different climatic and operational conditions. This is essential for validating experimental formulations, refining prototypes, or positioning a product within high-performance building strategies. Proper interoperability also reduces the likelihood that an innovative product will be replaced by a generic material during simulation. When data is clearly defined and consistently recognized by BEM engines, the resulting models reflect its specific characteristics rather than default placeholders. This strengthens confidence among decision-makers and enhances the credibility of comparative studies and optimization exercises. Ultimately, robust interoperability supports the broader adoption of novel material technologies by making their benefits visible, measurable, and repeatable across multiple digital tools. As we conclude this session, it is useful to step back and consider the broader message behind BIM/BEM interoperability. The transition from a physical description to an analytical model function as a data pipeline and the integrity of that pipeline determines how accurately materials are represented in energy simulations. The exchange formats used along the way play a significant role. Each carries its own strengths and constraints, and these differences directly influence how much material information survives into the final model. This is why well-prepared data, at the BIM stage, is so valuable. When materials are defined clearly, with validated thermal properties and a stable structure, they support a smoother transfer into GBXML, IDF, and other analytical environments. Centralized material libraries further reinforce this consistency, ensuring that all tools reference the same trusted dataset, minimizing discrepancies, and reducing the need for manual adjustments. This creates a more predictable and transparent digital workflow. Ultimately, interoperability enables credible performance evaluation, allowing innovative materials to be assessed fairly and accurately. By contributing structured, simulation-ready datasets, manufacturers not only strengthen the modeling process, but also enhance the visibility and impact of their technologies in performance-driven design. Before we conclude, I want to acknowledge the organizations whose technical resources supported this course. We thank Graphisoft and Autodesk for their BIM documentation, Design Builder for its insights into energy modeling workflows, and the U.S. Department of Energy for providing the foundational references behind EnergyPlus. Their contributions continue to shape the standards and practices that make BIM/BEM interoperability possible. Thank you for joining this course, and I invite you to continue with the next module. Welcome to the closing segment of Course 2.2, Building Digital Models and the Applicability of Construction Products. In this final section, we will reflect on the core ideas covered throughout the module and examine how digital models support performance evaluation and decision-making in construction. Throughout the course, we reviewed the foundations of building energy modeling, the differences between BIM and BEM, and how building geometry, material properties, and environmental inputs shape simulation results. We also explored the wider BEM ecosystem, from simulation engines to modeling interfaces, and examined the importance of calibration and BIM/BEM interoperability. This closing segment brings these ideas together, highlights the main takeaways, and points you toward further resources and upcoming opportunities within the Exploit for InnoMat training pathway. Let's begin. Let's revisit the main conclusions from this course. First, digital models are powerful tools for understanding how construction products perform in real building environments. They allow designers and researchers to test materials virtually and compare solutions under different conditions. Second, building energy modeling focuses on predicting building behavior, energy use, temperature evolution, and comfort, complementing BIM, which describes the physical components of the building. Recognizing this distinction is essential for managing data throughout the modeling workflow. Third, material and construction properties greatly influence simulation outputs. Thermal conductivity, density, heat capacity, and glazing characteristics all affect envelope performance and energy demand. We also explored how the BEM ecosystem includes simulation engines, visual modeling interfaces, climate tools, and specialized libraries, each contributing to different use cases and levels of expertise. Calibration helps align simulated results with real-world data, increasing confidence in model predictions. Finally, BIM/BEM interoperability supports efficient data exchange. Clean geometry, well-defined materials, and consistent system descriptions allow smoother transitions into the analytical environment and reduce modeling time. Together, these insights offer a strong foundation for applying digital models to evaluate construction products. To strengthen your understanding of digital modeling, here are several directions for continued learning. Introductory materials on building energy modeling provide useful context on building physics, simulation workflows, and typical modeling assumptions. Research on BIM interoperability explains the challenges of transferring data between platforms and offers strategies for improving accuracy. Exploring literature on calibration helps clarify how models are adjusted using real measurements, making simulation outputs more reliable and actionable. Documentation for major software tools such as EnergyPlus, OpenStudio, and Design Builder can guide you through practical modeling workflows, input structures, and common use cases. Climate-related and material characterization resources can also help refine model inputs and improve simulation quality. A full document containing all references and sources mentioned or used throughout this course will be provided separately for your convenience. Building energy modeling enables quantitative evaluation of material performance under realistic conditions. It helps identify how new products influence energy use, thermal comfort, and overall building behavior, key elements in product benchmarking and validation. The modeling workflows reviewed in this course, from geometry preparation to material definition, simulation setup, and calibration, help ensure that data is structured, consistent, and meaningful. Interoperability principles introduced here support the integration of material data, lab results, and design information into digital models, contributing to more reliable assessments. As you continue through the training pathway, these fundamentals will prepare you for more advanced modeling approaches, such as multiphysics, multiscale, and AI-assisted modeling that appear in later modules. Thank you for completing Course 2.2. Building Digital Models and the Applicability of Construction Products. We hope the concepts, workflows, and tools explored throughout the module have strengthened your understanding of digital modeling and its role in evaluating construction products. Your participation in External Course 2 contributes to a broader effort supporting innovation, sustainability, and digital transformation in the construction sector. We invite you to continue with the upcoming modules and to stay engaged with future training opportunities offered by Exploit for Inomat. Thank you once again for your time and interest, and we look forward to accompanying you in the next stages of your learning journey.